So we have the notes for section, 6.4, which deals with the fundamental theorem of calculus. So the fundamental theorem, the antiderivative part, says if f is continuous on some interval a to b, then the function capital F of x is equal to, from a to x, of some f of t dt. Has a derivative, so that the derivative of capital F is equal to the derivative of the integral, which is just a function with x plugged in. So example 1, find the derivative of this and the derivative of that using the fundamental theorem. Well, what the fundamental theorem just says is that the derivative and the integral are opposite operations, and you just plug the variable into your other variables. So this one would just become cosine x. This one would just become 1 over 1 plus x squared. And that's all you have to do. All right, so down here, it's a little bit different because we don't have an x, we have an x squared. Now, what this does is actually introduces a chain rule step. So when you do the derivative, so d dx from 1 to x squared, cosine t dt. So the first step is the same. The x squared goes in for the variable, so the cosine of x squared. However, that's not an x, so I have to multiply by its derivative as well. I have to take the derivative of that bound, so this can be times 2x. So your actual answer is 2x cosine x squared. Okay, so these are set up a little bit different. That trick only works if you have, so the reason these two are in here is that trick where you can just plug x in and multiply by the derivative if necessary only works if the number is the lower bound and x is the upper bound. Or in this case, we're going to have to split into two things. So the first thing I have to actually do here is reverse the bounds. And I do that by just putting a negative sign out front. Now it looks like it's supposed to. Number on the bottom, x on top. X just goes in for all the variables. This is equal to negative 3x sine x. Here, this one's going to be a little bit trickier because I have two variable bounds. So the first thing I actually have to do is I have to split it. And I can split it at any number I want. 0 works, 7 works, it doesn't matter. And then the second one's going to pick up at 0 and go to x squared. So that's actually the first step. Now this one's okay, number on bottom, variable on top, but this one is out of order. So this first one I actually need to reverse just like I did the first part. So from 0 to 2x, negative sign goes out front to reverse the bounds of 1 over 2 plus e to the t dt, plus from 0 to x squared, 1 over 2 plus e to the t dt. And now I can do my steps. So 2x goes in for t here, so 1 over 2 plus e to the 2x, negative out front, times 2, the derivative of the 2x, plus 1 over 2 plus e to the x squared, times 2x, the derivative of the x squared. So cleaning this up, negative 2 over 2 plus e to the 2x, plus 2x over 2 plus e to the x squared. Now, this 2 and this 2 and that 2 and that 2, they can't cancel because I don't have a 2 in front of the e. But that would be my answer. Okay, find a function y equals f of x with the derivative tangent that satisfies the condition. All right, so this is actually kind of a trick problem. So if I want the derivative to be the tangent, I'm just going to put my tangent, we'll use t, dt, inside, because if I take the derivative of an integral, it goes away. X has to go on top because I want my x to get plugged in. Now, if I know f of 3 is equal to 5, the easiest way to take care of this part is actually to put 3 down here. Because now when I plug 3 in for x, this integral part becomes 0, because if the bounds are identical, the whole integral goes away. So to make y equal 5 when x is 3, well, if this whole part is 0, I just need to add 5 to the end. So this function will have a derivative of tangent x, because if I take the derivative of the integral, x gets plugged in, so tangent x, derivative of number is 0, it goes away. But if I plug 3 into my original equation, the integral from 3 to 3 of tangent is 0. 0 plus 5 is the 5 I need. Okay, so then you got the fundamental theorem, the evaluation part. Says if f is continuous at every point of a to b, and if capital F is any antiderivative of little f on a to b, then this is the formula we use. Now this is kind of a variation of what we had last section, except we had an x here, f of x minus f of a, but this is how you can do evaluations for integrals. So example 5, evaluate from -1 to 3 of x cubed plus 1 using an antiderivative. So I need to figure out what capital F of x is first, the antiderivative. So when you do antiderivatives, I need the thing that would have a derivative of x cubed. Well, derivatives count down exponents, so antiderivatives count up the exponents. So it's going to become x to the fourth. Now the problem is, if I take the derivative of x to the fourth, I get 4x cubed. But I only have 1x cubed here. So what actually happens is the reciprocal of the new exponent goes out front, because 4 times 1/4 is 1, there's no coefficient. Now numbers, when you do their antiderivative, they become the coefficients and an x shows up. So this is technically 1x. So this is my function. So I need to figure out f of b, which would be f of 3. So 1/4 times 3 to the fourth plus 3. And I need to figure out f of a, which is the bottom number. So 1/4 times -1 to the fourth plus -1. So the top one, let's see here, 0.25 times 3 to the fourth, whoops, plus 3 is 23 1/4. On the bottom, 0.25 times -1, don't forget to put negative numbers in parentheses when you're doing your calculator, to the fourth plus -1. So this is -0.75. So it's f of b minus f of a, so it's 23 1/4 minus -0.75. So it's always a subtraction even though that number is already negative. So this is 23 1/4 plus 3/4, so that whole thing just comes out to be 24. And if I really want to check, I can use my calculator. So x cubed plus 1 from -1 to 3, 24. Same answer. But there may be the case where it says show your work, and then you can't just say, I used my calculator. Okay, area connection. So find the area of the region between the curve 4 minus x squared from 0 to 3 and the x-axis. So let's look at our graph. So 4 minus x squared will cross, if you look at the graph, it's going to cross at -2, +2, 1, 2, 3, 4. It's going to go up to, oh, I have to put 3 over here. So it's going to do something like this, and then come down here. So I'm only concerned about the part from 0 to 3, that part. So I need to find the area up here and subtract off the area down here. Or I could just do the whole thing all at once. So I'm going from 0 to 3 of 4 minus x squared dx. So antiderivative, so I need capital F of x. So numbers, just pick up x's. For this term, exponent counts up, reciprocal goes out front. So I need f of 3, which would be 4 times 3 minus 1/3 times 3 cubed. I need f of 0, which is 4 times 0 minus 1/3 times 0 cubed. So here we go. So f of 3 is going to be 4 times 3 minus 1/3 times 3 to the third is all just 3. Down here, that's just 0. So f of 3 minus f of 0 is 3 minus 0 is just 3. So the area is 3. Now, if I was talking about positive area, we'd have to actually break it into two things. We go from 0 to 2 and from 2 to 3 and find those values. So the other potential problem you could see would look like this. So from 0 to 2, 4 minus x squared dx. And then from 2 to 3. So you want to break it at where it crosses the axis, because what I'm actually going to do is take the absolute value of this number because I want it to be positive. So I, however, am going to use my calculator to do this. So 4 minus x squared from 0 to 2. So this area is 16/3. The second one, we'll just come up here and change the bounds from 2, 3. So if you notice, the calculator gives me a negative area. That's because it's below the axis. But if I want the total area, I just make it positive. So let's see here. 16/3 plus 7/3 is, so the total area would be 23/3 if you're talking about just area itself, not signed area. Okay, find the area of the region between the curve x cos 2x and the x-axis over the interval -3 to +3. So similar problem. So we're going to go from -3 to +3 of x cos 2x, and put our dx at the end. This one, since we've got goofy x times cosine x and everything else, I'm just going to let my calculator handle this guy. Now, just like before, what we're actually going to do is, since we want our areas to be positive, we're going to drop absolute value bars around it. We just want the total area. It doesn't matter whether it's above or below. So we're going to actually work this function out, not the original one. And we could have done the same thing up here. We could have just dropped absolute value bars around the 4 minus x squared. And that would give us the 23/3 as well. So let's see here. So integral of the absolute value of x cosine 2x, from -3 to +3 is, I'm just going to think for a while. I just have to look the answer up. If it thinks about it for too long. There we go. So it comes out to be about 5.43. So if you're finding total area, or just find the area of the region between, that's actually a total area problem. So total area is done by taking absolute values of the functions. So up here, if I look at this one again, if I do the integral of the absolute value of 4 minus x squared from 0 to 3, so I get 7.6 repeating, which is 7 2/3, which won't let me do it, but it is actually 23/3. This is, if you turn this guy into a decimal, it's 7.6 repeating. So you get the same thing. So total area, just drop absolute value bars around your function. Okay, so example 8 here, I believe it's the last thing. Yep. Okay, the graph of the continuous function f with the domain 0 to 8 is shown below. Let h be the function defined as the integral of, so the area below this curve. Find h of 1. So h of 1 would become integral from 1 to 1 of f of t dt, which is automatically 0 because the bounds are the same. It's h of 0, positive or negative. So that would be, I'm just looking at h of 0 would be from 0 to 1, from 1 to 0 of f of t dt. Now, if you look on your curve, between 0 and 1, the area of the curve is positive. It's above the axis. But I'm reading this graph backwards. These bounds are out of order. So this is negative, because it should be negative from 0 to 1 of f of t dt. And this part here is a positive number. It's above the axis. But since you're taking the negative of a positive, the whole thing comes out to be negative. Find the value of h of x for which h of x is the maximum. So I want to include the most amount of positive area I can, which would mean that I need to do the area up to that point. So x is equal to 4, because then I'm including all this positive area and none of this negative area. For which h of x is the minimum, well, this I want to include as much negative area as possible, which means I need to come all the way over here to 8. This gives me as much negative area as possible. Find the x-coordinates for all points of inflection. So this is where the graph turns. There's 3 places the graph turns. At x equals 1, right here. At x equals 3, right here. And at x equals 8. No, sorry, not 8, 6. There. Where the graph turns. Where the area changes signs. Okay, and that is the end of the section.